Good afternoon, class. Today I will be talking about acid-base equilibria. Here is the outline of discussion for our class today. First, I'll be talking about acids and bases, their definitions and classifications. Next, I'll be talking about pH and pOH, particularly on how to calculate the pH of strong acids and strong bases, weak acids and weak bases, and salts that undergo hydrolysis. And finally, how to determine the pH change in acid-base reactions. Third, I'll be talking about preparation of buffers, and under preparation of buffers, I'll be talking about two methods only. First one is reaction of strong acids and weak bases, or strong bases and weak acids. This one is pre-equivalence point. Next is mixing weak acid with its conjugate base, or salt of its conjugate base, or weak base and salt of its conjugate acid. And finally, I'll be talking about complex acid-base systems, particularly polyprotic acids and buffer preparation for polyprotic acids. Without further ado, let's start our lesson. First and foremost, acids and bases are defined using two definitions. Actually, there are three definitions, but in the context of our class, I'll be only introducing two definitions. The first definition is Arrhenius definition, which states that acids are compounds that produce hydronium ion in solution or in water when dissolved in water. And examples of those are hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrofluoric acid, so as long as there is ionizable hydrogen. And bases, on the other hand, are compounds that produce hydroxides in solution. So examples of those are hydroxide salts such as sodium hydroxide, lithium hydroxide, and potassium hydroxide. The other definition for acids and bases is the Bronsted-Lowry definition. According to the Bronsted-Lowry definition, acids are compounds that donate hydrogen ion, while bases, on the other hand, are compounds that accept hydrogen ion. The following equation shown here is that particular concept. So, in this case, hydrochloric acid donates its hydrogen ion to water to form hydronium and chloride ion. In the other equation here, we have ammonia accepting hydrogen ion from water to form ammonium cation and hydroxide ion. In Bronsted-Lowry definition, we have to take note of two terms. One is the acid and base. So the acid is the one that donates hydrogen ion. So in the first equation, we have hydrochloric acid as the acid and water as a base. What is formed when a base accepts the hydrogen ion of an acid is what we call the conjugate acid. And what is formed when an acid loses or donates its hydrogen ion is the conjugate base. In Bronsted-Lowry definition, there is the acid and conjugate base pair and base and conjugate acid pair. In equation number 2, we also have the same instance. Our base in this context is ammonia and acid is water since it donates its hydrogen ion. So the base produces a conjugate acid, which is ammonium cation, and the acid also produces a conjugate base. A student learning about acid-base equilibria should remember these two terms because these two terms will recur in this particular topic. Now, we will classify acids and bases based on their strength. So there are two types of acids and bases. One is strong acid and strong base, or weak acid and weak base. So what's the difference between strong acids and strong base? We'll be talking about that later. Examples of strong acids are, we have the 7 strong acids here. So remember all these 7 strong acids because apart from these 7 strong acids, all other acids are already weak acids. So the 7 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and finally we have sulfuric acid here. For the hydroxide bases, on the other hand, we have sodium hydroxide, potassium hydroxide, lithium hydroxide and rubidium hydroxide. And also we have cesium hydroxide for the alkali metals. We also have hydroxides of alkaline earth metals, which are barium hydroxide, strontium hydroxide, and calcium hydroxide. So these are the 8 strong hydroxide bases. All other hydroxide bases are already weak bases. Okay, but what are the properties of strong acids and strong bases? The answer for that is they fully ionize in solution. So if you have hydrochloric acid dissolved in water, it fully ionizes to hydrogen ion and chloride ion. Or since this one is in water, so hydrogen exists as hydronium ion. Since it is fully ionized in the solution, then they are stoichiometrically equivalent. Therefore, if you have 1 mole of hydrochloric acid, you also produce 1 mole of hydrogen ion and 1 mole of chloride ion. So it goes to follow that if you have 1 molar of hydrochloric acid, you also have 1 molar of hydrogen ion and 1 molar of chloride ion. Similarly, that also follows for strong bases. Strong bases such as barium hydroxide, when ionized in water, will produce barium cation and hydroxide anions. Since there are two hydroxide ions, two hydroxides that are bound to barium, then upon dissolution in water or upon ionization, there are 2 moles of hydroxides that are produced. So therefore, if you have 1 mole of barium hydroxide, upon dissolving in water, you produce 1 mole of barium cation and 2 moles of hydroxide anions. Similarly, if you have 1 molar of barium hydroxide, then you also produce 1 molar of barium cation and 2 molar of hydroxide anions. How about properties of weak acids and bases? So unlike strong acids and bases, weak acids and bases only partially ionizes. So there is no full ionization. Suppose in the case of acetic acid, so the first equation is that of acetic acid. So acetic acid, when dissolved in water, will ionize to acetate ion and hydrogen ion. But we could not say that if there is 1 mole of acetic acid that is ionized in water, 1 mole of acetate ion and 1 mole of hydrogen ion is also produced. So we cannot say that because the moles of acetate ion and hydrogen ion is not stoichiometrically equivalent to that of acetic acid due to the fact that there is only partial ionization. We could not say that if we have 1 molar of acetic acid, you will also produce 1 molar of acetate ion and 1 molar of hydrogen ion. So we could not say that. Similarly, in the case of weak bases, for example, in equation number 2, we have ionization of ammonia in water. So ammonia produces ammonium ion and hydroxide ion in water. But the moles of ammonium ion and hydroxide ion is not stoichiometrically equivalent to that of ammonia, and therefore we cannot say that if you have 1 molar of ammonia, then you will also produce 1 molar of ammonium and hydroxide ion. So we cannot say that. What determines the ionization or the extent of ionization of weak acids and weak bases is what we call the Ka and Kb. Ka for weak acids and Kb for weak bases. Ka is a shorter term for acid dissociation constant, whereas Kb is the base dissociation constant. The Ka and Kb expression is equal to the concentration in molarity of the ions that are dissociated. For example, we have acetate ion and hydrogen ion divided by the concentration in molarity of the undissociated weak acid. Ka is just basically the ratio of the dissociated products or dissociated ions and undissociated starting materials or reactants. That is also true for Kb. We have molar concentration of ammonium multiplied by the molar concentration of the hydroxide ion divided by the molar concentration of undissociated ammonia. So the greater the value of Ka, the stronger is the weak acid. So therefore, if there is a weak acid that has a Ka of 1 times 10 to the negative 2, and another weak acid that has a value of Ka value of 1 times 10 to the negative 5. Therefore, the weak acid that has the greater Ka value, which is 1 times 10 to the negative 2, is the stronger acid. Next, we'll be talking about pH and pOH. pH and pOH is the measure of acidity and basicity. The following diagrams show the relevance of pH and pOH in acidity and basicity. Any compound that has a pH value that is greater than 7 is said to be basic, and any compound that has a pH value that is less than 7 is said to be acidic. A pH value of 7 is what we call a neutral pH. Similarly, any compound that has a pOH value that is greater than 7 is said to be acidic, and any compound that has a pOH value that is less than 7 is said to be basic. So it's just the opposite of pH. Same here, pOH 7 is also the neutral pOH. But in mathematical terms, pH is just the negative logarithm of the hydrogen ion concentration, whereas pOH is the negative logarithm of the hydroxide ion concentration. So the greater the value of the hydrogen ion concentration, the lower the pH value. That is also true for the pOH value. But why does water have a neutral pH? Okay, so in solution, or when water is used as a solvent, the sum of pH and pOH is equal to the pKW. And Kw is just the ionization constant for water. So is water a weak acid or a weak base? So from the previous examples, water can act as both an acid and a base. So in this context, water is said to be amphiprotic. So amphiprotic can act as both an acid and a base. So consider the following equation below. So we have two molecules of water that react with each other will produce hydronium ion and hydroxide ion. So one of these molecules of water donates its hydrogen and one of the molecules of water accepts the hydrogen ion. Okay, the dissociation constant for water is what we call the Kw. And Kw is just the product of the molar concentrations of hydrogen ion or hydronium ion and hydroxide ion. The Kw is already determined experimentally, and the value of Kw is 1 times 10 to the negative 14. So from this value, we can calculate the concentrations of hydrogen ion and hydroxide ion in water, which is 1 times 10 to the negative 7 for the hydrogen ion or hydronium ion, and 1 times 10 to the negative 7 for the hydroxide ion. So that is the reason why the pH of water is 7 and the pOH of water is also 7. Because naturally, water dissociates to hydronium ion and hydroxide ion, but at very low concentrations, which are these values. So we could say that the value of pKw is also equal to the sum of the values of the pH and pOH in solution. So therefore, pKw is 14. Okay, let's apply the concept of pH and pOH in calculating the pH and pOH of strong acids and strong bases. Okay, let's have the first example provided here. The first example is the dissociation of hydrochloric acid in water, which produces hydrogen ion and chloride ion. So therefore, if you have, since this one is a strong acid, all of the species are stoichiometrically equivalent. So all the species are stoichiometrically equivalent. So therefore, if you have 1 times 10 to the negative 3 molar for hydrochloric acid, it also follows that the concentration of the dissociated species are also the same. So therefore, we can calculate immediately the pH of strong acids by plugging in its original concentration. So pH is the negative logarithm of hydrogen ion concentration or hydronium ion concentration, which is 1 times 10 to the negative 3 molar. And therefore, we can calculate the value of 3. So the pH of 1 times 10 to the negative 3 molar hydrochloric acid is 3. Okay, how about pOH? Can we calculate the pOH of strong acids? The answer is yes. when there's pH, there is always a corresponding pOH value. So take note that in a solution, pH plus pOH is equal to 14. So therefore, pOH is just 14 minus pH. So we have already calculated the pH. So we could say that pOH is 11. And from here, a pOH value that is greater than 7 is acidic. So it also corresponds with the previous diagram that I have shown. Okay, how about for bases? In the second equation, we have dissociation of barium hydroxide in water, which produces barium ion and two hydroxide ions. So since this one is also a strong base, then all the species are stoichiometrically equivalent. We have 1 times 10 to the negative 3 molar of barium hydroxide that produces 1 times 10 to the negative 3 molar of barium ions and 2 times 10 to the negative 3 molar of hydroxide ions. So take note, it is 2 because there are 2 equivalents or 2 moles that are produced. So we can calculate the pOH value from the hydroxide ion concentration by plugging its value to this formula. So pOH is equal to negative log of 2 times 10 to the negative 3 molar, and the value is 2.70. Also, we can calculate the pH. pH is just 14 minus pOH, and 14 minus 2.70 is equal to 11.30. Okay, how about in the case of weak acids and weak bases? So we cannot immediately determine the concentrations of hydrogen and hydroxide ions for weak acids and weak bases respectively due to the fact that there is a partial ionization. So a double arrow shows a partial ionization. So how do we calculate the value of pH and pOH for weak acids? So in that case, we have to make use of the Ka value. The Ka value and the Ka expression is this one. We have molar concentration of the ionized species and the molar concentration of the species that are not ionized. And Ka is already experimentally determined for each weak acid. So the Ka value for acetic acid is 1.8 times 10 to the negative 5. First, I would like to teach you about the ice table. So ice table is used in calculating the pH of weak acids and weak bases. So ice table stand for initial, change, and equilibrium. What happens when acetic acid partially ionizes to acetate and hydrogen ion is that as acetate and hydrogen ion are produced, they also form back the unionized acetic acid. So there is a double arrow reaction here in which the reactant forms the product and the product forms back the reactant. But there is a middle line in these two reactions, and that is what we call the equilibrium. So the equilibrium is the state in which there is an equal formation of reactant and equal formation of products. So in order to calculate the pH of weak acids and weak bases, we have to calculate the equilibrium concentrations of each of the species involved. So initially, we don't have acetate and hydrogen ion because before the dissociation, there are no acetate and hydrogen ion produced. And during the change, or we don't know how much was ionized in the reaction, so let's just assign negative x molar. So we don't, because we don't know how much of the concentration of acetic acid was ionized, so let's just say negative x, and how much of it was produced, we also don't know. So it is plus x molar and plus x molar. So the change tracks how much was ionized and how much was produced. But we don't know these values, so let's just assign x to them. Okay. Therefore, at equilibrium, we have 1 minus x molar as the concentration of the acetic acid and x molar as the concentration of acetate, also x molar for the concentration of hydrogen ion. The next thing that we have to do is to make use of the Ka expression. The Ka expression is this one. So the Ka expression makes use of the equilibrium concentration of each of these species. So therefore, we have Ka is equal to acetate ion and hydrogen ion divided by acetic acid. Okay, but we have determined that concentration of acetate and hydrogen ion is X, and that of acetate is 1 minus X. The value of Ka is also experimentally determined, and that is 1 times 10 to the negative 5. Okay, we can make use of quadratic formula. In this context, if we evaluate this expression, we will get a quadratic equation which is equal to x squared is equal to 1.8 times 10 to the negative 5 minus 1.8 times 10 to the negative x. 1.8 times 10 to the negative 5x. So we can calculate the value of x using quadratic formula. So first, let's just calculate the value of x using the quadratic formula. Transpose all these terms into the left side of the equation to get an equation that is equal to ax squared plus bx plus c is equal to 0. Okay, so now we have an expression that is equal to ax squared plus bx plus c. So in order to evaluate the value of x, we can use the quadratic formula, which is equal to x is equal to negative b plus minus square root of b squared minus 4ac over 2a. But this one is too tedious, so let's just use an online quadratic formula calculator. Okay, using the quadratic formula calculator, we get a value of x that is equal to 4.23 times 10 to the negative 3. Since x is equal to the hydrogen ion concentration, therefore the hydrogen ion concentration is also equal to 4.23 times 10 to the negative 3 molar. And we can calculate the pH of the solution afterwards. So pH is just equal to negative log of the hydrogen ion concentration, and just plug in the value of x. And finally, we can calculate the pH of the solution. Okay, the pH of the solution is therefore 2.37. This is by using the quadratic formula. But we can calculate the value of x without using the quadratic formula. So we can evaluate whether or not x is negligible by dividing the initial concentration to that of the Ka value. The initial concentration is 1 molar, and the Ka value is 1.8 times 10 to the negative 5. And we get a value of 5.56 times 10 to the positive 4. One thing that you have to remember here is that if you get a value that is 10 to the 2 or greater than 10 to the 2, meaning x is negligible. But if you get a value that is less than 10 to the 1, meaning x is not negligible. Okay, what do we mean by saying x is negligible? By saying x is negligible, that means we can just cancel this x here because it does not affect much the the initial concentration, and we can evaluate this expression like this. Okay, therefore, we can calculate for the value of x by taking the square root of the Ka value. So we can calculate the value of x, and that is 4.24 times 10 to the negative 3. Okay, previously, we've had 4.23 times 10 to the negative 3. So it does not affect the calculation that much. Okay, therefore, the concentration of hydrogen ion in this context is 4.24 times 10 to the negative 3 molar. And finally, we can calculate the pH by taking the negative logarithm of the hydrogen ion concentration. Okay, just plug in the value. The pH is therefore 2.37, which is equal to that of when using the quadratic formula. Okay, the next thing that we will be discussing is calculating the pH of weak bases. So let's have this example. In this example, ammonia is dissociated in water and produces ammonium ion and hydroxide ion. Similar to that of weak acids, weak bases also have a dissociation constant which is equal to Kb, or the base dissociation constant. So the base dissociation constant expression in this context is this one, the product of molar concentrations of dissociated species divided by the undissociated species concentration in molarity. The value of Kb is also determined, and that is 1.8 times 10 to the negative 5. Suppose we have 1 molar of ammonia here. In order to solve this, we can use the ice table once again. Initially, we don't have ammonium and hydroxide ions. As the equation goes on, some of the ammonia is dissociated, but we don't know how much, so let's just assign X molar. And some of the ammonium is produced and hydroxide is also produced, so we have plus X molar for ammonium and hydroxide. The equilibrium concentration is therefore 1 minus X molar, and we have X molar and X molar here. Using the Kb expression, we can just substitute the equilibrium concentrations of each of the species here. So for the ammonium, we have X. For the hydroxide, we also have X. For the ammonia, we have 1 minus X, and the value of the Kb is 1.8 times 10 to the negative 5. Okay, in order to make our lives easier, let's just solve whether or not X is negligible. So is X negligible? Okay, if we calculate 1 divided by 1.8 times 10 to the negative 5, we get a value of 5.56 times 10 to the negative 10 to the positive 4. So therefore X is negligible. And since X is negligible, we can just cancel this one. And we get a value of X squared is equal to 1 times 1.8 times 10 to the negative 5. You just take the square root of both sides and you get a value that is equal to 4.24 times 10 to the negative 3. Take note that this value is equal to the molar concentration of hydroxide. So therefore, the concentration of hydroxide is also 4.24 times 10 to the negative 3 molar. And from the concentration of hydroxide, we can calculate the value of POH, which is negative log of 4.24 times 10 to the negative 3. And we get a value that is equal to 2.37. But if you're asked to calculate the pH, then the pH is equal to, we already know that pH plus POH is equal to 14 in aqueous solution, or when the solvent is water. So therefore, pH is equal to 14 minus POH, and 14 minus 2.37 is equal to 11.63. Okay, so this is how you calculate the pH of weak acids and weak bases. But how about the pH of hydrolyzing salts, or salts that undergo hydrolysis? Before we proceed on the calculation of pH of hydrolyzing salts, let us identify what are hydrolyzing salts in the first place. In acid-base reaction, the products of acid-base reactions are always salt and water. So if you have an acid and a base, the product is always salt and water. So suppose you have a strong acid and strong base. What you produce is a salt derived from the reaction of strong acid and strong base. So an example of that would be in the reaction of hydrochloric acid with sodium hydroxide, you produce sodium chloride. So salts that are produced from the reaction of strong acids and strong bases tend to produce a neutral solution. They produce a neutral solution because they do not undergo hydrolysis. On the other hand, salts that are produced from the reaction of weak acid and strong bases, like this one, tend to undergo hydrolysis. So for example, if we have acetic acid acetic acid is a weak acid, reacted with a strong base, sodium hydroxide. So what is produced is sodium acetate. So sodium acetate undergoes hydrolysis and produces a basic solution afterwards. Okay, later on, I will show you how hydrolysis works. Similarly, when weak bases are reacted with strong acids, they also produce salt that undergo hydrolysis. So when weak acids and bases are reacted with strong acids and bases, they form salt that undergo hydrolysis. So for example, in this scenario, if we have strong acid hydrochloric acid reacting with weak base ammonia, it produces a salt called ammonium chloride. So ammonium chloride undergoes hydrolysis and produces an acidic solution. We can also react weak acids and weak bases to form salts of weak acids and weak bases, but the product or the calculation for the pH of these salts would tend to be very tedious and complicated, and this is not often done in titration, so we need not concern ourselves with salts of weak acids and weak bases. Okay, but how does hydrolysis occur? So, hydrolysis of salts are only applicable for salts of weak acids and strong bases, or salts of strong acids and weak bases. Let's have the following examples. So, the first scenario here is that we have a salt of weak acid and strong base. So, the weak acid is acetic acid and the strong base is sodium hydroxide. So, since these are salts, then they are ionized completely. Upon ionization in water, what is produced is sodium ion and acetate ion. But the acetate ion undergoes further reaction, this one. Acetate ion reacts with water in a process called hydrolysis to produce acetic acid, and the excess hydroxide is the reason why salts of weak acids and strong bases produce basic solution. So here, salts of strong bases and weak acid produces basic solution for the reason that there is an excess hydroxide that is produced after the hydrolysis of the salt. So hydrolysis is just the reaction with water. Water is reacted by the conjugate base. This one is a conjugate base, and therefore it produces acetic acid and hydroxide ion. Similarly, in the context of strong acids and weak bases, or salts of strong acids and weak bases, when ammonium chloride, which is a salt of ammonia and hydrochloric acid, is ionized in water, what is produced is ammonium ion and chloride ion. But it is the ammonium ion that produces, or that further reacts with water. So this reaction with water is what we call hydrolysis. And this hydrolysis reaction will produce ammonia and hydronium ion. The excess hydronium ion is the reason why the resulting solution becomes acidic. Okay, but how do we calculate the pH of hydrolyzing salts? Suppose we have a 1 molar sodium acetate salt. Okay, what is the pH of the solution? So, in this context, when this salt is dissolved in water, it will completely ionize to sodium ion and acetate ion. Therefore, all the species are stoichiometrically equivalent. So this one is 1 molar, this one is 1 molar, and this one is also 1 molar. But what happens next is that acetate ion will react with water in an acid-base reaction, or in a hydrolysis reaction to produce acetic acid and hydroxide ion. Okay, so we have this equation here, and we can calculate the value of the hydroxide ion, or the concentration of hydroxide ion, using the ice table. So we have 1 molar here. This one is, water is not counted. This one is 0, and this one is 0 initially. So this one is minus x plus x, and this one is also plus x. Therefore, at equilibrium, we have 1 minus x molar. This one is x molar and x molar. Okay, this one is just the reverse of the dissociation of acetic acid. So the dissociation of acetic acid, this one, has a Ka value of 1.8 times 10 to the negative 5. But since this one is reversed, and in this context we have this one as a base and this one is a conjugate acid. So since this one is a base, then we should make use of the Kb expression and not the Ka. But how do we calculate the Kb expression of the conjugate base of acetic acid? In order to calculate the Kb expression for the conjugate base, we must remember the following formula. So we have Ka times Kb is equal to Kw in water. Kw is just 1 times 10 to the negative 14. And Ka is the acid dissociation constant for the acetic acid. So therefore, Kb is just equal to Kw over Ka. We already know the values for the Kw and Ka. Ka is 1.8 times 10 to the negative 5. And therefore, we can calculate the value of Kb. Okay, therefore, the value of Kb is 5.55, 5.56 times 10 to the negative 10. From the Kb expression, we can say that the Kb expression is acetic acid and hydroxide ion concentration and molarity over acetate ion. Okay, water is always not included. Substituting the equilibrium values, we get x times x over 1 minus x is equal to 5.56 times 10 to the negative 10. Okay, the next question is to decide whether or not x is negligible. So is x negligible? Okay, we have 1 divided by 5.56 times 10 to the negative 10, and we get a value that is equal to 1.8 times 10 to the positive 10. So it is a very large value, and therefore x is negligible. So we can just cancel x here, and we get a value of x squared is equal to 1 times 5.56 times 10 to the negative 10. Taking the square root of those value, and we get a value that is equal to 2.36 times 10 to the negative 5. So since x is equal to the hydroxide ion concentration, then we can get the pOH value. And that is equal to negative log of 2.36 times 10 to the negative 5, 4.63. Therefore, the pH is equal to 14 minus 4.63, and that is 9.37. The pH of this hydrolytic salt is 9.37, and that is a basic solution. Okay, we can also do the same for the ammonium chloride salt, but I won't be showing that anymore. Okay, how about calculating the pH change in acid-base reaction? So we can calculate the pH change in acid-base reaction, and this is already shown in the previous resources that I have shared in the Google Classroom. But anyway, we can calculate the pH change in acid-base reaction. So initially, we have, before the reaction, we have 1 molar of hydrochloric acid. Okay, the pH of 1 molar hydrochloric acid is 0 because negative log of 1 is 0. But after addition of 50 ml of 1 molar sodium hydroxide, how much is the pH change? So we can calculate the pH change by determining the concentration after the reaction. We have 0.1 molar here, 0.1 mole here because this one is 0.1 liters, and 1 liter times 1 moles per liter is 0.1 moles, whereas this one is 0.05 moles. Sodium hydroxide is the limiting reagent, so therefore it is the one that is exhausted first. So during the reaction, we have negative minus 0.05 moles, minus 0.05 moles, and plus 0.05 moles of sodium chloride produced. So after the reaction, you don't have moles of sodium hydroxide already, but we currently have 0.05 moles of hydrochloric acid remaining, and that is the excess reagent. Okay, so how do we calculate the concentration in molarity of hydrochloric acid after the reaction? So all we need to do is to divide it by the total volume, and the total volume is 100 plus 50 is 150 ml, and that is molarity of HCl after the reaction is equal to 0.05 moles divided by 0.150 liters, and we get a value that is equal to 0.333 molar. Okay, so therefore the concentration or the pH of the solution after the reaction is 0.48. Okay, pH is equal to negative log of 0.333, and therefore it's 0.48. Thus, the pH change is 0.48 minus 0. This one is after the reaction, and this one is initially, before the reaction. So the pH change is 0.48 pH units. Okay, how about for weak acids and weak bases? Okay, if a weak acid and weak base is reacted with strong acid and strong base, Then we can also calculate the value of pH afterwards. So suppose we have acetic acid reacted with sodium hydroxide to produce sodium acetate and water. Okay, suppose we have 100 ml and 1 molar. This one is 50 ml and 1 molar. Okay, before the reaction, during the reaction, and after the reaction. Okay, we have 0.1 mole here, and we have 0.05 mole before the reaction. So therefore, sodium hydroxide is the limiting reagent. During the reaction, sodium hydroxide is exhausted first. So we have 0 moles here, and we have 0.05 moles here. But we also produce 0.05 moles of product. Okay. The concentration after the reaction is equal to 0.05 moles divided by 150 ml in liters is 0.150 liters. So 0.150 liters. And therefore, the concentration after the reaction is 0.333 molar. Same here, 0.333 molar. Take note, what is left after the reaction is we have acetic acid and sodium acetate. But acetic acid is a weak acid, so we can calculate the pH of weak acid using the ice table. So we have acetic acid dissociates to acetate and hydrogen ion. So we can use the ice table here. And the initial concentration of acetate is 0.333 molar. For here, we also have the product which is 0.333 molar. So one is 0. So change is x plus x, and this one is plus x. Therefore, after the reaction, we have the equilibrium concentrations of each of the species to be 0.333 minus x molar, and for the product, we have 0.333 plus x molar and x molar. The next thing that we have to do is to calculate the value of x using the equilibrium constant expression. So equilibrium constant expression, or the Ka, is the concentration of the acetate and the concentration of hydrogen ion divided by the concentration of acetic acid, and these are 0.333 plus x, and we have x from here, and we also have 0.333 minus x, which is equal to the value of Ka, and the value of Ka is 1.8 times 10 to the negative 5. So in order to make our lives easier, we can just decide whether or not x is negligible. So is x negligible? Okay, we have the initial concentration, which is 0.333 divided by the Ka value, and we get a value that is equal to 1.85 times 10 to the positive 4. Okay, so therefore x is negligible. So we can just cancel all these x's, and what we have here is 0.333 times x over 0.333. Now we can also cancel these two terms, and we get the value of x to be equal to 1.8 times 10 to the negative 5. Now we can calculate the pH of the solution after the reaction. So we have pH that is equal to negative log of 1.8 times 10 to the negative 5, and we get a value that is equal to 4.74. Okay, but there is an easier way to calculate the pH of a weak acid and conjugate base system. So how do we do that? We can do that using the Henderson-Hasselbalch equation. How is the Henderson-Hasselbalch equation derived? Okay, suppose we have a hypothetical equation for a weak acid, Ha ionizes to H plus and A minus. And therefore, the Ka value would be this one, or the Ka expression would be this one. Okay, taking the negative log of this expression, the negative log is what we call the P value, or the P function. So negative log of Ka is equal to negative log of the expression above. But based on the rules of logarithmic function, suppose we have log of AB or A times B, log of AB is equal to log of A plus log of B. So from these rules on logarithmic functions, we can divide this logarithmic expression here, and we get an expression that is equal to log of Ka is equal to negative log of H plus log of A minus over HA. Take note that negative log is what we call P. So this one is pKa and this one is pH plus, and we have minus log of A minus over HA minus HA. So rearranging the equation, we get an expression that is equal to pH is equal to transposing this one over there, and we get an expression that is equal to pH is equal to pKa plus log of A minus over log of over HA. So this is what we call the Henderson-Hasselbalch equation, which is derived from the expression of Ka. The Henderson-Hasselbalch equation works on the assumption that x is negligible. If x is not negligible, then the value that is given by the Henderson-Hasselbalch equation becomes erratic, or the value becomes wrong. In order to make use of the Henderson-Hasselbalch equation, we have to decide first whether or not x is negligible. Okay, let's make use of the Henderson-Hasselbalch equation to answer the given on the previous problem. Take note that Ka is given, the concentration of A minus and HA is given. A is the conjugate base, and this one is the acid. So we have pH is equal to pKa. pKa is negative log of 1.8 times 10 to the negative 5 plus log of the concentration of the conjugate base. Conjugate base is the acetate, this one, conjugate base, and this one is the acid. So each concentration is 0.333, 0.333 divided by 0.333. So we have 4.74 here plus log of 1. But take note that log of 1 is 0. So therefore, pH is equal to 4.74. Okay, so that is how we use the Henderson-Hasselbalch equation in order to solve the pH of a weak acid and conjugate base system.